In this video, we will obtain the statistical model of the output of the demodulator in a digital communication system. In particular, we will obtain the conditional distribution for the observation Q at discrete instant n when the symbol that is transmitted in the same instant is one of the symbols of the constellation, in general the symbol of index I. Now, the kth coordinate of the observation is given by the inner product between the received signal and the kth element of the orthonormal basis. For the ease of notation, we consider n equal to 0 here, and in this case the integral is in the first symbol interval, from 0 to the time symbol duration capital T. Here we have also considered that the basis in the modulator is adapted absolutely with respect to the channel, and this means that the received signal is equal to the addition of the transmitted signal and the noise. We have a perfect adaptation between the channel and the modulator. With this assumption, now we can replace here the expression for S of t by the linear combination given by the coordinates of the symbol and the elements of the orthonormal basis, phi j, and now we can define here the kth coordinate of the noise as the inner product between the noise and the kth element of the orthonormal basis. In this expression here, we can move this addition of the coordinates out of the integral. In the integral, we have the definition of the inner product between the jth and the kth elements of the orthonormal basis. This is 0 for j different than k because we have orthogonal functions, and in this addition we only have the term associated to j equal to k. Therefore, what we have here finally is that the kth coordinate that we have in vector q is equal to the kth coordinate of the transmitted symbol plus the kth coordinate of the noise, given by the inner product between the thermal noise and the kth element of the orthonormal basis. Therefore, in vector q at discrete instant n, what we have is the coordinates of the symbol that was transmitted in the same instant plus the n coordinates of the noise. This is called the equivalent discrete channel. The relationship between the symbol that we have here, the vector representation of the symbol at the input of the modulator, and the vector representation of the received signal at the output of the demodulator is given by this relationship. We have the symbol that was transmitted, but a noise vector with capital N components. Now we are going to obtain the statistical model for the coordinates of this noise vector z. These coordinates are the coordinates of the thermal noise in the different element of the basis. N of t is a Gaussian random process, so these coordinates will be jointly Gaussian random variables with a jointly Gaussian probability density function. And the parameters of a jointly Gaussian density function of a multidimensional Gaussian PDF are the vector of means with the mean of every coordinate and the covariance matrix containing the covariance of each pair of these coordinates. If now we compute the mean of every coordinate, the mean of the kth coordinate is the expected value of the inner product between the noise and the kth element of the basis. This is a deterministic function. We can move this out of the expected value, and in the expected value we only have the expected value of the thermal noise, and thermal noise has 0 mean. Therefore, all these coordinates have 0 mean. With respect to the covariance between the jth and the kth coordinates, taking into account that we have 0 mean random variables, we can obtain this covariance as the expected value of the product between Cj and Ck complex conjugated. This is Cj, this is Ck complex conjugate. The two elements of the basis are deterministic, can go out of the mathematical expectation as well as the integrals because of the linearity of the mathematical expectation. Inside of the mathematical expectation, we have the definition of the autocorrelation function of the noise at t minus tau, because we have an stationary random process, which is n0 halves delta of t minus tau. Then in this integral, the integration with respect to tau, we are integrating a delta. This means that we evaluate this signal at tau equal to t. We have this expression here, and then in this integral, finally, we have the definition of the inner product between the basis functions phi k and phi j. This is 0 except for the case j equal to k. Therefore, we have n0 halves when j is equal to k and 0 in any other case. As the covariance is 0 for different coordinates, these coordinates are uncorrelated for Gaussian variables. This means that they are independent, and we have that the variance for each component is equal to n0 halves. So the coordinates are independent, and all of them have Gaussian distributions with 0 mean and variance n0 halves. This is the statistical model for every coordinate. And the joint distribution, taking into account the independence, is just given by the product, and we have a multidimensional Gaussian with 0 mean and variance n0 halves in every direction, in every dimension. Taking into account that in the observation Q we have the addition of the transmitted symbol plus this vector of noise components, the conditional distribution of Q given a known transmitted symbol is just a Gaussian distribution whose mean is now the coordinate of the corresponding symbol, and the variance is n0 halves. This is the conditional distribution for every coordinate of Q. The joint distribution for all the coordinates is just a multidimensional Gaussian whose mean is the symbol that is transmitted, and the variance in every dimension of the space is n0 halves, and we have independent components in the n dimensions. And in summary, this is the conditional distribution of the observation given a transmitted symbol. A Gaussian distribution, n-dimensional, the mean is the transmitted symbol, the variance in each dimension, we have independent components, the variance in each dimension is n0 halves.